Today we shall discuss the concepts of energy and power in electromagnetic waves. As we have already pointed out, in an electromagnetic wave, there is an electric field and magnetic field oscillating 90 degrees with respect to each other. Since we know electromagnetic waves carry energy, we can associate this energy to both electric field and magnetic field. Instead of talking about energy itself, it's more convenient to introduce the concept of energy density. So the energy density associated with the electric field is given by half times epsilon naught, which is permittivity of vacuum, assuming that this wave is propagating in vacuum, times the square of the magnitude of the electric field. Likewise, there is an energy density associated with the magnetic field, and it is given by the following expression: half 1 over mu naught, where mu naught is the permeability of vacuum, times the square of the magnitude of the magnetic field. So the total energy density of this electromagnetic wave is simply the sum of U sub E plus U sub B. Both these U sub E and U sub B are energy densities. Thus, the unit is joules per cubic meter. Since the magnitude of the electric field is related to the magnitude of the magnetic field by the following expression, and C squared is quite simply 1 over mu naught times epsilon naught, where C is speed of light in vacuum, one can show that this expression is indeed the same as U sub E, namely the energy density of electric field. To show that, all we have to do is to substitute 1 over mu naught from this expression, and that would become epsilon naught C squared. And C squared B squared from this expression is quite simply E squared. Like that. And you see it is the same as U sub E. So you have equal contribution from the two fields as far as the energy density is concerned. If we want to calculate the energy instead that is contained within a certain volume of space in which the electromagnetic wave is propagating, all we have to do is to take the energy density, U sub T, the total energy density that is, and multiply that with a particular volume, and that would give you the amount of joules contained in that volume, namely the amount of energy. Let's quickly illustrate this concept using this simple example. Let's assume we have a particular electromagnetic wave, and suppose its electric field magnitude is 100 volt per meter. We want to determine the energy density of this electromagnetic field. Since we already know the magnitude of the electric field, you can use the expression of the energy density purely in terms of electric field, and that is simply that. Now epsilon naught is 8.85 times 10 to the power minus 12, and the magnitude of the electric field is given to be 100, so you just square that, and which will give you the final answer of 8.85 times 10 to the power minus 8 joules per cubic meter. Assume that you have this field, the electric field with that much magnitude, is contained within a certain volume of space, and the volume of this space is, say, 2 cubic meter. Then the amount of energy contained within that volume is quite simply that number times that, which will give you 1.77 times 10 to the power minus 7 joules. Of course, the concept of energy density, energy, can be related to the concept of power through Poynting vector, which we have discussed in our previous video. To better illustrate this, let's look at a couple of examples. Example 1. At a distance of 100 meters, 100 kilometers rather, from a radio station antenna, the electric field amplitude is 0.08 volts per meter. Assuming that the antenna radiates equally in all directions above the ground, find the total power output of that station. So that is the ground, and let's assume that the radiation emerges from there. So at a distance of, let's say, 100 kilometers, and it is radiating equally, so we can assume that the radiation spreads spherically like that, creating a volume of semi-sphere, because the source is on the ground. The power output, as we have mentioned a few minutes ago, can be expressed in terms of the average value of the Poynting vector. So, S average, remember the unit for the magnitude of a Poynting vector is given by watts per meter squared. So in order to get watts from a Poynting vector, you have to multiply that with some sort of an area. The average value of a Poynting vector can be written as 1 over 2 mu naught the amplitude of the electric field times the amplitude of the magnetic field. Now what about this area? This area is the area of that semi-sphere. This is a three-dimensional radiation. An area of a sphere is given by 4 pi radius squared. So for a semi-sphere, then it is just 2 pi r squared, where r, the radius, is 100 kilometers. These two are related because E naught is C B naught. We know E naught, so we can calculate B naught. So let's quickly calculate B naught. B naught is E naught over C. E naught is 0.08. C is 3 times 10 to the power 8, and that's going to give you 2.67 times 10 to the power minus 10 Tesla. Substituting this in here, E naught is 0.08, mu naught is 4 pi times 10 to the power minus 7 in SI unit, and r, the radius, is simply 100 kilometer. You have to change that into meter, so 100,000 meter. Don't forget to square. After substituting these numbers, we get the following for the total power output. Namely, the total power output is 5.34 times 10 to the power 5 watts, or quite simply 534 kilowatts. And that solves the problem. Problem number 2. Assume that 12% of the power input to a 100-watt lamp is radiated uniformly in all directions as light of wavelength 550 Newton meter. Find the electric field amplitude and magnetic field amplitude for that light at a distance of 4 meters from the source. So 12% out of that 100 watt is just 12 watts. That is the power that is being radiated. And as we have seen, this power equals the average value of the Poynting vector times certain surface area. Now, if you assume the light source is here and it's radiating, so that is the spherical wave that results. So the radiation is spherical in all directions. So that means the surface area that we are dealing with here is 4 pi r squared, where r is the radius of that particular surface. In this case, 4 meter, because that is the distance from the source that we are concerned with. The average value of the Poynting vector is given as 1 over 2 mu naught, the amplitude of the electric field times the amplitude of the magnetic field. And we know E naught and B naught are related in the following manner. Substituting E naught in terms of B naught, we get C B naught squared for S average. Let's put in all this information in here. That equation right there, power is 12 watts, S average is 1 over 2 mu naught, C B naught squared, A is 4 pi r squared. So mu naught is 4 pi times 10 to the power minus 7, r is 4 meter. And solving, we should be able to find B naught, which will give you 2.24 times 10 to the power minus 8 Tesla. and that is the amplitude of the magnetic field. The amplitude of the electric field can be found from C times B naught, and that's going to give you 6.71 volts per meter, where C is the speed of light in vacuum, namely 3 times 10 to the power 8 meter per second. And that solves the problem. Thank you for watching.